In this talk, I want to introduce you to our recent work where we use continuous time Monte Carlo methods for Bayesian model and variable selection. And this is joint work with Joris Birken, Sebastiano Grazzi, and Frank van der Meulen from Delft University of Technology. And we have introduced something we call the sticky piecewise deterministic Monte Carlo method and want to introduce it. So in Bayesian statistics, often is the task to sample from a posterior distribution, because by sampling we can learn answers to our statistical questions. So here is a prototypically posterior distribution mu over a parameter vector x, and you see that this is parameterized as unnormalized negative log density psi with respect to the high-dimensional Lebesgue measure dxi. And then there is an unknown normalization constant. And in this talk, we are not interested in densities with respect to the Lebesgue measure, but we have a variable selection problem, and each variable might either belong to the model or not. And we express this in terms of a prior distribution, which has a continuous component dxi for each coordinate, and then a discrete component, a Dirac measure at 0, which tells us that a priori each of the variables might be 0 with a certain probability. And then there's still the density, and now it's a density, a negative log density psi with respect to this product of Lebesgue and Dirac masses. So where is this interesting? Typical situation where this pops up is in sparse Bayesian inference problems. I have already alluded to this. So I have a parameter vector x. Many of these entries x1 up to xd are perhaps 0, but I don't know which ones. I have data and a log likelihood L of x. So L is negative psi, and I have not given the data a letter here. And then, because that's a high-dimensional problem, just estimating x without prior information is not suitable. So there's some need for regularization or inductive reasoning. And if we know that many of these parameters are 0, then this is a form of regularization. So it might help us to recover the truth. And furthermore, we are also interested in which parameters are 0. It tells us which parameters belong to our model and what a suitable model is. So this is an interesting statistical question. And then there might be additional prior knowledge about smoothness scales. So for example, if x is the entries of x are the pixels of a picture, then we might know that the pixel color only changes continuously over the range of the picture. So a typical way to approach this in Bayesian inference is to assign a spike and slab prior. So the slab is a continuous component. Pi is just a density, a prior density on my coordinate xi. But then there's also a weighted Dirac mass at 0, which tells me that with a certain probability the coordinate xi does not belong to the model, which is saying that it is 0. So the probability for that would be 1 minus wi here. And then the problem is to sample from the posterior, which is then proportional to the density times the prior measure. And here the prior is of product form, but maybe there's additional information about smoothness, as I indicated. And then you would have a prior which itself is given as a density with respect to such a product measure. And so how do we approach this? Our tool for this is continuous time Markov processes. Monte Carlo methods in continuous time. I have drawn here a picture of a trajectory of a piecewise deterministic Markov process. So it moves in space along a sampling time axis. So a discrete sampler would have a first sample, a second sample, a third sample, but a continuous sampler has a continuous trajectory exploring the distribution which it targets. I have drawn the distribution here, the density, the continuous part, and the direct part to the side. And piecewise deterministic means it moves along deterministic trajectories. But once in a while, a random event happens which might change direction or location of the process. So from this picture, not immediately visible, there's a position coordinate and a direction coordinate, and the deterministic dynamics are given as ordinary differential equation. And the random times are tuned in a way that the process preserves the measure, has the measure as invariant measure. So if it moves too far into the tails, it has to change direction and go back. So if the only random events which can happen are reflections, then you can show that you preserve the stationary measure when you your instantaneous reflection probability in a certain point is related to the gradient of the negative log density psi times the velocity. So if you're moving very fast in the wrong direction, you better return. And this is you show that this preserves then the measure with density psi by showing skew detailed balance. So in a metropolis Hastings, if you show detailed balance, then you would have random walk behavior. But here you move up until you turn around, and then moving down, you're moving down with a negative speed and moving up with a positive speed, and you have to balance the parts where you're moving up with the parts where you're moving down. So you can only achieve skew detailed balance. And then what's our idea? So we want to sample a Dirac measure at 0. And the basic idea is pretty simple. Every time you pass 0, you spend a random time delta there, and we just take exponentially distributed random time with expectation 1 over kappa I. That's easy difficult. So it's easy to say that this is the dynamics of my process, but it has turned out that it's not so easy to show that this is just the right thing to do. So before doing that, or indicating how we do this, let's look at some examples. But so essentially, for each of the coordinates of the process, every time I'm passing by in 0, I'm spending their exponentially distributed time, and then I continue the trajectory in the same directions. So there's something skew symmetric. So you're not just turning back, but you're keeping your momentum even if you have made a break. And with such a trajectory, you can answer the statistical questions. So, for example, if you want to know what's the probability that a certain coordinate does not belong to the model, we run the trajectory for a long time t and measure the time proportional it has spent in 0. That is the answer to our posterior probability that the coordinate is 0. Related to this talk, we have a Julia package, Zig-Zag boomerang, which contains implementations of these algorithms. And these are general purpose implementations. So if you have a model, you have the negative score, the gradient of the negative log likelihood times prior, and the kappa I giving the weight to the Dirac masses, then you're in business. And there's a nice feature about these procedures. You only need an unbest estimate of the negative score to get a valid procedure. So it is time for some illustrations. So my first example is a picture noisily observed, and the problem is to find the signal in the noise, and you can already see visually what the signal might be here. This is an artificial example, but this is an interesting problem also in a very practical application. So there are many pixels, and we know that most of them are black or zero, and there's a small connected region containing a signal of interest. And then this induces our posterior measure mu if we choose the appropriate weight for the probability that the pixel is zero, appropriate continuous prior component, for example a smoothing prior, and the likelihood is then given from the independent noise on each pixel. So having sorted all that out, we run our sampler, and a sampler trajectory. You have seen a one-dimensional one where each of the coordinates moves in space up and down, and every time it passes zero it spends a time there, and nothing else happens here, only that I'm getting a coordinate for each of the pixels, and they are moving up and down, not independently because there's some smoothness constraints, so they are more likely to turn around together if they're getting too far away from each other. And here you see the posterior mean as the mean of the occupation of the long trajectory, and you see that posterior spends a lot of time in the black pixels, for those pixels which are really black, and recovers the region of interest. A second example, you have a stochastic differential equation describing interacting, and these are not particles but little entities, and each of the entity moves a stochastic trajectory which is biased towards moving to their secret love interest. So each of these points, a void, has a secret other void which they are following, and then there's a third void which they are avoiding. And the sample from the observation would look like this. So maybe this void is in love with that one, but it is very difficult to see. So statistical methods, for example, putting a spike and slap prior on the matrix of love and hate interest might help here, or does help, as we show in our paper. And the third example, workhorse example from Bayesian inference, is sparse logistic regression, where you have a linear model which determines the prior odds, and you have binary observations. So this is a third domain where these methods are applicable, and we try this out. So I have a short time to explain a bit how we show that our proposed procedure of just waiting an exponential time every time you pass in a coordinate at zero means that we introduce the Dirac component in the measure mu. And so if you want to do that, we have to first properly write down what our process is, and we start defining the deterministic flow, and we like to work with operators script x telling us how a test function f changes in an infinitesimal time under the flow. That's the first ingredient. The second ingredient is that we have the Poisson rate lambda, which tells us what's the probability that there's a reflection event or a random event in the next infinitesimal time, and that means that our events are from an inhomogeneous Poisson process. And the final ingredient is the transition kernel, which tells us what happens once the bell rings and the Poisson process gives us an event. Then there's a transition kernel Q, which tells us about the change in the state. For example, there might be a deterministic reflection happening. And all these together give the generator of the process, and the generator is a way to describe our sticky piecewise deterministic process in infinitesimal form. And that is of particular interest if we want to show that it preserves a certain measure. We just have to show that it is stationary for a very short time. So, for example, we start with the Zig-Zag sampler. We write down the state space, position, and velocity component. We start with the process targeting the measure with negative log density with respect to the big measure. And the Zig-Zag process has deterministic dynamics, so it moves at constant speed in a certain direction. The random events which might happen depend on the partial derivative of the psi function in the direction I'm moving. And finally, the transition kernel Q for each of the coordinates, it just says that I'm doing a deterministic flip of the i's component of the velocity. So my notation here says that I'm changing the i's velocity coordinate to its negative. And then I can write down the generator of the Zig-Zag process. Deterministic dynamics, random events, and then the change of a test function under the momentum flip. And if I want to write down what the sticky Zig-Zag does, then I'm just have to describe what happens if my process reaches zero. And to describe this in a Markovian way, we are splitting up the state space in a way that there's a positive and a negative zero. So there's now two copies of zero. And if we approach zero from the left-hand side, then we spend some time in it, and then we move to the right-hand side zero. That's just to make everything Markovian. And then our generator is just the old one with a special rule for what happens if we approach zero. And then the task is first to describe that this process has is a well-defined process. So just writing down a generator, we still have to show that there's a corresponding process to it. And we can do this. We are following the approach in Davis, and we find that this is actually a very nice process, a Feller process. And then the final step is to use our knowledge about the generator to show that the process preserves the stationary measure for a very short time. So that's the nice aspect about working with the generator. Then we have a accessible formulation of what characterizes a stationary measure, and that is that the generator applied to a test function f integrated over the stationary measure is zero. And doing that, we can indeed show that our process as defined has the right stationary measure. Thank you.